Introduction to Binary Search Trees. And today, we're going to look at fundamental data structure that is used extensively in computing, uh, which is binary search trees or BSTs. A binary search tree is a node-based binary tree that organizes data with efficiency. Each node in a binary search tree contains a unique key and two subtrees, as you can see, termed as left and right. Important rule of binary search trees is that the left subtree contains only nodes with keys less than the parent node's key, while the right subtree only nodes with keys greater. This property is crucial and ensures that operations such as search, insert, and delete can be performed quickly. Purpose and applications of BSTs. So binary search trees are more than just a theory. These trees have real world applications that impact everyday technology. Binary search trees are ideal for implementing dynamic sets and dictionaries where quick search, insertion, and deletion of items are crucial. They are also used in priority queues where elements are continuously added and removed. Outside of abstract data types, binary search trees serve practical purposes in database indexing and network management, facilitating fast data retrieval and efficient storage management. Properties of binary search trees. So if we were to focus on some essential properties of binary search trees, the most fundamental property is binary tree property, which means that the tree remains ordered, and this facilitates efficient traversals and operations. And also, each node in a BST uniquely appears, avoiding any duplicate values. Understanding the depth and height is also important for analyzing the performance of BSTs. Just to give a brief overview of what depth and height we're talking about here. For depth is the number of levels from the root to the node, and the height is the longest path from a node to a leaf. Searching in a BST. So when searching for a value in a BST, we begin at the root and make a series of decisions. So if the value is less than the current node's key, then you want to move to left. If the key's value is greater than root's value, then we want to move right. And we are, as you can see from this code example as well, you want to continue this process recursively in a subtree until you find the value or exhaust the possibilities. And the efficiency of this operation depends heavily on the tree's height, while average case being logarithmic of O of log n. And in the worst case, you will have O of n if your tree is unbalanced. Insertion in a BST. So insertion in a BST follows a similar logic to searching. You want to start at the root, and then you would want to find the appropriate position for the new node so that the binary search property is maintained. Let's say we want to insert a value 10. If key is 10, we would want to compare 10 with the root. And based on the comparison, if root value is greater than 10, then we would want to recursively call insert on left. If the root value is less than key, then we want to insert to right and do this for insert recursively until we find an empty spot where 10 can be inserted as a new node. Deletion in a BST, unlike search and insertion, deletion is a little more complex and comes in 3 varieties. First would be deleting a leaf node. Second would be a node with 1 child. Third would be a node with 2 children. So each scenario requires different strategies to maintain the BST properties. Deleting a node with 2 children is the most challenging. Typically, we find either the maximum element in the left subtree or the minimum in the right subtree to replace the deleted node. So if we take a look at this example, delete node, we will have a base case to see if root is none, then it returns root. But if key is less than the value of the root, then we will recursively call delete node on the left side. Otherwise, we would call delete node on the right side. Otherwise, that means the key is same as the root's value. Then we will be deleting that node, and there are cases we need to take care of. This is the first one is root left is none. Then we are setting root right as temp, and then we're deleting root to be by setting it to none, and we are returning this temp value. Also, if root right is none, we are returning this temp value for root left. If node has 2 children, then we would need to find the in order successor, which is the smallest in the right subtree. So we will need to have another function mean value node, and then copy the in order successor's content to this node, and then delete the in order successor. Tree traversals and applications. So traversals are methods to visit all the nodes in a BST. In order traversal, what it does is it visits nodes in non-decreasing order. This is useful for sorting. Pre-order and post-order traversals are helpful if you for deep copies of trees or for binary tree evaluations. Level order traversal, because it goes level by level using a queue, it is excellent for visualizing tree structures. Complexity and limitation. So we looked at BSTs, and while BSTs are efficient, the performance can degrade to linear time when they become unbalanced. In order to address this, balanced versions of binary search trees like ABL trees or red-black trees maintain a stringent balance, ensuring that operations always run in logarithmic time of log n, and these structures adjust themselves during insertions and deletions to maintain balance. Conclusion. So understanding binary search trees is essential for anyone who are in software development field, and these structures form the backbone of efficient data handling in numerous applications. So I strongly encourage you to explore by implementing your own trees and look further into balanced binary search trees. That's everything for this lecture. Thank you everyone for listening.